International Nickel, the leading producer of this unique metal, has been a world leader for more than 50 years in solving the many problems caused by corrosive action. INCO's extensive program of research and development with nickel-containing and other materials has greatly advanced the science of proper selection of materials for structures, equipment, and products. The knowledge gleaned over many years at INCO's product research facilities in North America and Britain has played a major role in helping man to overcome the ever-present natural forces of deterioration. In nature, the forces that cause corrosion are as relentless as the surge of the sea. Corrosion turns structures and machines into crumbling skeletons and piles of junk. It turns gleaming buildings into useless shells. In the United States alone, it is estimated that corrosion costs over $10 billion a year. Different metals are affected to varying degrees, and corrosive attack takes many forms. Attack may be by general tarnishing or rusting, with occasional perforations in highly affected areas. The metal may suffer highly localized attack by pitting. Even hard, tough metals can crack as a result of corrosion. Deterioration may be confined to crevices, under gaskets, or in sockets. Corrosion can also have the effect of removing one of the constituents of an alloy, leaving a weak residue. It is the purpose of this film to explain how corrosion occurs and some of the things that can be done to stop it. The basic cause of corrosion is the instability of metals in their refined forms. Because of this free energy relationship, the metals tend to revert to their natural states through the processes of corrosion. In the case of iron, the action of rain forms rust. When you analyze rust, you find it is iron oxide. When you analyze natural iron ore, you find it too is iron oxide. In rusting, iron has simply reverted to its original native state. The basic nature of corrosion is almost always the same. A flow of electricity between certain areas of a metal surface through a solution capable of conducting an electric current. This electrochemical action causes destructive alteration or eating away of metal at areas which are called anodes, where the electric current leaves the metal and enters the solution. We have the presence of an electrolyte as one of the first requirements of corrosion. An electrolyte is any liquid that contains ions. Ions are electrically charged atoms or groups of atoms in solution. Pure water, for example, contains positively charged hydrogen ions and negatively charged hydroxyl ions in equal concentration. Our corrosive environment may be any form of moisture ranging from plain water to the strongest acid or the strongest alkali. It may be just moisture condensed from the air, or it may be salt water. But in any environment, regardless of its nature, the basic mechanism of corrosion is in principle the same as the electrochemical action in an electric dry cell such as we've all seen. There is always an electrolyte, an anode, and a cathode where current enters the metal from the electrolyte. These electrodes may consist of two different kinds of metal, or they may be different areas on the same piece of metal. In either case, there must be a potential difference between the two electrodes or areas so that electricity will flow between them. A wire or other metallic path is necessary to complete the circuit for the flow of electrons, which are negatively charged particles moving in the wire from the negative to the positive electrode. The popular concept of current flow, as used in this discussion, visualizes imaginary positive charges moving in the opposite direction. This electron path may be provided by any kind of conductor or merely by the fact that metals are in contact with each other. Let us consider what takes place at the anode when corrosion occurs. Remember that the anode area is that point, by our popular concept, that the current enters the solution. Several things happen simultaneously at this location. Positively charged atoms of metal detach themselves from the solid surface and enter into solution, while the corresponding negative charges in the form of electrons are left behind in the metal. The detached positive ions bear one or more positive charges. Each iron ion carries two charges and releases the electrons which travel through the metal to the cathode area. What has been taking place at the cathode all this time? As you can see, the electrons reaching the surface of the cathode through the metal have been meeting and neutralizing some positively charged hydrogen ions which have arrived at the same surface through the electrolyte. In losing their charge, the positive ions become neutral atoms again and may combine to form molecules of hydrogen gas. The reduction of hydrogen ions results in the accumulation of a relatively high concentration of OH ions, which are left behind to increase the alkalinity at the cathode or make the solution less acid here. The formation of hydrogen in this type of anode-cathode corrosion cell can be shown by placing a piece of ordinary iron in a solution of hydrochloric acid. A vigorous formation of hydrogen bubbles is seen. Under such conditions, the metal corrodes very quickly. The usual dissolution of the metal is occurring only at the anodes, with hydrogen bubbles forming only at the cathodes, even though it may appear that they are being released all over the surface rather than at well-defined cathodic areas. The anodic and cathodic areas shift from time to time. This permits substantially uniform corrosion to occur. If we could see this action through a powerful microscope, we would see many tiny anode and cathode areas on the surface of the metal. These areas are often extremely small and so numerous as to be almost inseparable. There are many causes for this, such as inclusions in the metal, lack of homogeneity, surface imperfections, orientation of grains, localized stresses, and also variations in environment. If we could see just one anode and one cathode in a giant view, we would see electrons released by the formation of each ferrous ion flowing through the metal from the anode to the cathode, where they meet the hydrogen ions in solution, which act as electron acceptors at the cathode surface. One electron is accepted in the discharge of one hydrogen ion. The hydrogen then appears as hydrogen gas coating the metal surface. As this process continues, oxidation and corrosion of iron occurs at the anodes, and plating out of hydrogen occurs at the cathodes. This formation of hydrogen molecules and the evolution of hydrogen gas are the principal reactions in corrosion by acids. Reactions involving oxygen dissolved in the electrolyte can also occur to complete the cathodic reaction. Oxygen can react with the accumulated hydrogen to form water, and by removing it, may permit corrosion to proceed. In doing this, oxygen acts as a cathodic depolarizer. As such, in neutral solutions where the hydrogen ion content is quite low, the concentration of dissolved oxygen and/or its availability are usually the rate-controlling factors in the corrosion reaction. The products of the anode and cathode processes frequently meet and enter into further reactions that yield many of our common visible corrosion products. For example, with the corrosion of iron and water, the hydroxyl ions from the cathodic reaction, in their migration through the electrolyte toward the anode, encounter ferrous ions moving in the opposite direction. These ions combine to form ferrous hydroxide. This soon becomes oxidized by oxygen in solution to form ferric hydroxide, which precipitates as a form of iron rust, with which we are all too familiar. Depending on the alkalinity, oxygen content, and agitation of the solution, this rust may form either away from the iron surface or right next to it, where it can exert more of an influence on the further progress of corrosion. The action of oxygen in furthering corrosion can also be demonstrated by placing iron turnings in two flasks filled with water. We'll allow oxygen to bubble through the water in one flask to supply it with oxygen, and we'll saturate the second flask with nitrogen, which drives oxygen out of solution. After they bubble for 2 or 3 hours, we'll find that the iron in the oxygen-free nitrogen solution is as bright as ever. But the iron in the water saturated with oxygen has already begun to rust. One of the causes of corrosion is differences in the electrical potential of dissimilar metals coupled together and immersed in an electrolyte. The resulting attack on one of the metals is known as galvanic corrosion. When we consider galvanic corrosion, it is essential to know which metal in the couple will suffer the accelerated corrosion. This is indicated in a rough way by the positions of metals in the standard electromotive series. Hydrogen is used as an arbitrary reference element. As we move up the list from hydrogen, one after another, the metals become increasingly reactive. Similarly, as we go down from hydrogen, the metals become increasingly inert. For example, if we put a piece of potassium in water, we get a violent reaction. Whereas, we can place a piece of platinum in strong nitric acid with no evidence of attack. The electromotive series also shows which metals can displace other metals in solution and suffer corrosion in the process. Any metal may displace one below it in this series. For example, iron can displace copper from solution, with the copper ions acting as the acceptors for electrons in the corrosion of the iron. The displaced copper appears as a coating on the corroded iron surface. Similarly, hydrogen ions can act as electron acceptors for any metal above hydrogen in the electromotive series, as in the case of zinc in hydrochloric acid. Metals below hydrogen in the series do not readily displace hydrogen from solution and therefore are more resistant to corrosion, as in the case of copper dipped into the same hydrochloric acid as the zinc. But copper can displace silver from solution, with the silver ions here acting as the electron acceptors in the corrosion of the copper. This electromotive series holds only for metals in particular concentrations of their own salts. In other electrolytes, the performance may be different. In studying galvanic corrosion, we use instead of the electromotive series a somewhat similar galvanic series based on experience with combinations of metals in seawater. Similar galvanic series can be developed for other environments. In any couple, the metal near the top of this series will be the anode and suffer the accelerated corrosion in a galvanic couple, while the one nearer the bottom will be the cathode and receive some galvanic protection. This means that any given metal may be an anode or a cathode, depending on the other metal with which it is coupled and their galvanic relationship in the environment encountered. Now the question is, what determines the speed at which galvanic corrosion will proceed? One factor is the relative difference in electric potential between the two metals. To illustrate, zinc coupled with aluminum in sodium chloride solution will generate a potential of about 300 millivolts, whereas with zinc and copper in the same solution, the potential is over 700 millivolts. The greater the potential difference, the greater will be the driving force behind the galvanic corrosion. As the galvanic corrosion reaction proceeds, the initial potential or driving force diminishes, and the potential of the anode drifts toward that of the cathode, and that of the cathode drifts toward that of the anode. This change in potential is called polarization. That at the anode, anodic polarization, and that at the cathode, cathodic polarization. In certain corrosion reactions, the polarization that occurs at the cathodes exerts more of a controlling influence than the lesser degree of polarization at the anodes. Consequently, in these cases, what happens at the cathode has greater practical importance. However, these cathodic reactions do not proceed with equal facility on all metal surfaces. As a result, some metals polarize more readily than others. It is necessary to know something about polarization characteristics as well as initial potentials before one can predict the extent of galvanic corrosion with any particular couple of metals. A direct example of this effect on galvanic corrosion is provided by an experiment in which pieces of steel of the same size are connected in an aerated salt solution to pieces of copper of different sizes, one large and one small. Both couples generate current, but notice, the couple with the large cathode produces the higher current. Thus we can see that it is hazardous to connect a small anode to a larger cathode. The following experiment further emphasizes this point. Here at INCO's Francis L. Lequy Corrosion Laboratory at Wrightsville Beach, North Carolina, one of the world's leading facilities for studying corrosion in marine environments, we are taking from test in seawater riveted plates that have been immersed for several months. One of these plates consists of two pieces of steel joined by copper rivets. As we uncover the copper rivets, we see that they are in good condition and that there is no significant acceleration of the corrosion of the steel in their immediate vicinity. Now let us see what has happened to the steel rivets used to join the two copper plates. Here the steel rivets have been attacked very severely. The metals are the same in each case, but the unfavorable area relationship of the large copper cathodes and the small steel anodes was responsible for the severe galvanic corrosion of the steel rivets. The same type of cell that develops between two different metals may also develop on a single metal surface. Differences in potential from point to point can be created by differences in environment. Oxygen concentration cells can be set up to cause cathodes to develop at the areas of high oxygen concentration, and anodes where corrosion occurs at the areas of low oxygen concentration. The fact that electricity does flow between points where oxygen concentrations differ may be demonstrated with similar pieces of steel in each side of a two-compartment cell containing a dilute sodium chloride solution. No current flows when they are coupled through a microammeter, but if we bubble nitrogen through one side of the cell to reduce the oxygen concentration and oxygen through the other side to increase the oxygen content, we find electricity flowing with the steel and the electrolyte starved of oxygen acting as the anode, thus proving the existence of a corrosion current. Similar corrosion currents can be generated by differences in metal ion concentrations. The existence and location of anodes and cathodes in an oxygen concentration corrosion cell on a steel surface can be demonstrated by the changes in color of certain reagents as well as by the use of electrical instruments as in the preceding experiment. We have shown that the cathode reaction produces an increase in the concentration of hydroxyl ions as a result of removal of hydrogen ions or the reduction of oxygen. Phenolphthalein is a well-known indicator which develops a red color when the concentration of hydroxyl ions is increased to the point where the solution becomes alkaline. Therefore, if phenolphthalein turns red as corrosion proceeds, it will detect the existence of a cathode and reveal where it is. Similarly, potassium ferrocyanide is a reagent which produces a blue color by reaction with ferrous ions formed at anodic areas when iron corrodes. The appearance of this blue color, therefore, demonstrates the existence and location of anodes on iron. Using these reagents, we can show the development and location of the anode and